All right, here we are going to get back started on our statistics. We have just come back from break and we had done probability before break. We'll revisit that because at the end of this unit, we will have a units 5 and 6 combined test. So we'll be pulling those ideas back. So if for some reason you did not master that, then still continue to work on that or uh, get into some tutorials with me so that we can get some of that stuff that you did not do well on clarified by the end of this unit. Okay, random variables and sampling distributions. Two different things. Really, random variables goes with probability, but it we didn't really have enough time to stick it in before the break, so that's why it ended up coming over into this unit. Okay, here we go. So we had talked about that discrete random variables, those binomial, when we did binomial, and we saw those histograms, okay? And then we had taken those probabilities and kind of estimated those or approximated those with a continuous distribution in the normal model, okay? So just in general, we know that we have a random variable because it's something that comes out in an experiment or something where you cannot predict the initial what's happening. Like when I toss a coin, I do not know what that next result is going to be. Okay, so I cannot predict with certainty. It varies from coin toss to coin toss, but in the long run, there is a predictable outcome. Okay, predictable. So, when I open up a box of light bulbs, I do not know how many of those will be defective. But if I opened many, many, many boxes of light bulbs, then in the long run, I would see a pattern and I would see a trend and I would see on average how many seem to be defective out of a box of 100 light bulbs. So it's important to keep that law of large numbers. If you do many trials, many, many trials, then that cumulative probability, it will settle down to that true probability, the law of large numbers, you see. So let's remember that that's what's happening with these random variables, that we see what is happening and we have an expected value in the long run. Okay. Now, just real quick, want to revisit this idea of discrete versus continuous. Those discrete events were a finite, countable amount of options. So like you can have the numbers, a finite amount of shoes in your closet. You can't have 3.4 shoes. I don't think so, unless you have a part of a flip flop or something. Now you might be able to have 3.5 pair of shoes. Okay, but even still, that's your only option. 3, 3.5, 4, 4.5, 5, 5.5, until you can fill that closet up or you have enough spaces. So another example of a discrete random variable could be like the amounts that can be won in a game. $1.50 could be won, $2, $5.35, or $10. See, even though I have decimal values, I still have 4 possible outcomes. A discrete, countable, finite amount of outcomes. Okay? So it's not entirely correct to say, oh, it's a whole number amount. The outcomes aren't whole numbers, but yes, I have a finite 4 possible outcomes. Okay, 3 possible outcomes. So you do have a whole number amount of possible outcomes. Okay. And then, of course, with continuous, it's infinite. It can be any of these little bitty decimal finite. You can hit a dart on a dartboard in just like all these infinitely many small places, and it's not a countable, really a countable amount. Okay. Take a look at these, see if you think they are discrete or continuous. And we'll take a look at those over here. Here we go. Number of desks in a classroom, discrete. You can only get so many in there. And plus, there's only so many that can fit and be legit doable in a classroom. Okay. How about the average number of desks per classroom in a Texas high school? See, if I took the average per classroom, then I can have decimal amounts. So once I have turned it from the number of items into the average amount, now I have a continuous situation. So that's kind of what's happening when we're turning a discrete into a continuous. Fuel efficiency can be in little finite amounts. Continuous. What's the next one? The person that throws a baseball, you throw a baseball a certain distance. I think that's a continuous amount. And then how about the number of questions on an exam? Statistics final exam, discrete. Okay. All right. So now we're going to play a game. And in class, I give everybody $5. Okay, let me see if I can't get my cards out. I got my cards. I got my money out. And we're going to say, so unfortunately, the remote students or people who are not here do not actually get to play this. So here we go. So everybody gets $5. Okay. And then when they get $5, then they can buy a free assignment in Canvas. Okay. So there can be a day that you don't have to do your homework or whatever. So it's a free homework pass. All right. So, you want to have to do one of the reflections or something. So that'd be nice. So here are the rules of the game. Here I have a full deck of cards here. I probably need to check these out before tomorrow and make sure that it is a full deck because I'm not trying to be tricky here. Okay. So what happens is you have to pay me $5 to play. Okay. So somebody comes up, decides that they want to play this game. So everybody's starting with $5. So essentially, I guess, I'm giving everybody one free assignment for this unit. So that's cool. Okay. So everybody gets one free assignment. Okay. We're starting off with that. And so then somebody, if they decide to play, then they're going to pay me $5. Okay. And then they're going to draw a card from the deck. And here's what they can win. Here we go. If you get the Ace of Hearts, which has happened, let me make sure it's in here. Yep, there it is right there. If you get the Ace of Hearts, then you will get back. So you pay me $5, but then you get the Ace of Hearts, and then I'm going to give you $100. Oh, I don't have I don't have any hundreds, but I'll give you two 50s. So I'll give you $50 or $100 back. So keep in mind, in essence, really what happened, you gambled one free assignment, and then I gave you back 20 free assignments. So technically, how much did you net when that occurred? Technically, here's you, and then I give you this. Technically, you're only ahead $95. Okay, so do keep that in mind. All right, next thing. You can pay me $5, play the game, and if you get one of the other aces, so how many other aces are there? I want to make sure they're all in here. There are 3 other aces. Okay, so since there's 3, I see 1, 2, 3. Okay, I see the other 3 aces in here. Then you get $10. So you gave me 5, and then I will give you 10 back. So you benefited $5. You got 2 free assignments. Okay, and then the last one of where you can win something. You pay me $5, you get a heart. Okay, of which, the Ace of Hearts, that's the big winner. So how many other hearts are there? So there are 12 other hearts. Okay, and so if you do that, then if you get another heart, I'm going to give you your $5 back. So you've really just broken even. Okay, you gave me an assignment, and I gave you one back. Okay, that's how the game is played. But guess what? Any other card, anything else, then you gave me your $5 and that's it. You lost it. Okay. So you gambled and you lost. And now I do not have to give you a free assignment during this unit. Okay. So let's play the game. So I asked people during class, and a lot of them raise their hand to play. And because of time, then I just pick the first three hands that I see. And so three people get to play the game, and we go through the game and they play it. And let's talk about what happens. What do you think is going to occur? How often are people going to win back that $100 and actually get those 20 assignments back free? Okay, so here we go. Who wants to play? All right. So this idea of events happening, and then the probability of those events happening, because hopefully you can guess that what's happening is the payback of getting $100 is very unlikely because you only have 1 out of 52 chance of getting that ace of hearts, and so on. So this probability event and then the payback that occurs because of that probability happens in every industry. Everything from, of course, casinos, we've already talked about that, to sports betting, stock market events. And then, insurance industry is all over this because they know an actuarial science is a field of study where you are predicting or you are putting those probabilities to certain events, like the probability of a major injury, the probability of a minor injury, the probability this will occur and this will occur, and then the amount of payout for that event. Therefore, insurance companies will be able to know on average about how much they have to pay back per client. And when that happens, then they can set their rates so that they may be paying out this much per client on average, but they'll take in more than they end up paying out so that they can guarantee that in the long run, they will make a profit. Okay, that's the big idea, and that is huge. So let's take a look at exactly how that looks with this particular game. So, of course, with this game, is it discrete or continuous? So hopefully you could see that there were 4 possible outcomes. You get 100, you get 10, you get 5, or you lose. Discrete. Okay, a countable finite amount of options. All right. Now, so we're going to talk about this. It is actually important that when we make a probability table and a probability distribution, which I've got right here. So when we make that table, we want to pay attention to the view, the viewpoint. Is this about what Miss McClellan has to pay out, or is this about what the student benefits? Is it from the view of what Miss McClellan gets, or is it from the view of what the player profits or the player has to pay? So this one has been defined as let X equal the amount of profit, because if I'm the one making this game, I'm the one who in the long run is going to profit. Okay. So anyway, the amount that I will profit per play of the game. All right. So let's take a look at the payoffs. So the payoffs, here we go. Let's take a look at that. So on that, and I think I'm just going to do this. This is easier. So when we have those payoffs, then we can see this. Look at what is happening here. Okay. And I'm going to, oopsie. Okay, so let's make another one of these guys so I can kind of hide some stuff. All right, here we go. So here are the options that could happen. Okay, we're going to get an ace of hearts. Okay, so think about it this way. If there's an ace of hearts, then I will take in $5. That's why this is a positive 5. Okay, but I will take in $5, but then I have to pay out 100. Then I lose 100. So overall, my net profit is negative 95. Now, how often does that happen? That only happens 1 out of 52 times. That's the probability of that negative 95 occurring. Okay, next. Then we say, okay, any of the other aces. So there were 3 other aces, so that's telling me that that's going to be 3 out of 52. Okay, but here's what was happening. You were paying me $5, so I got in $5, so that's a positive 5. I got $5, but then I had to pay out 10, so then I lost 10. So overall, my net is minus 5. Okay, any of the other hearts, so there's 12 other hearts. So you see where we are so far. So there's 12 other hearts, and with that, you give me $5, I give you $5 back. So it's a break-even situation, and that happens 12 out of 52 times. Okay, for everything else, you gave me $5. I kept it because you lost. So that's $5. But how frequently does that happen? Well, everything else. And everything else is 52 cards minus the 16 ways already accounted for in the first 3 boxes here. So there were 16 ways that you could win, 36 ways you could lose, win or break even. Okay, so this is called a probability distribution, a discrete probability distribution. And so then what we do with this is we see, okay, so what does this mean on average per play is happening? So this is what is on your formula chart. And let me show it to you in a clear form. So this is on your formula chart. Discrete random variable. It says probability distribution. So look at here, this mean. This is a very scary looking formula, but you have to actually understand it because you do have to show the work, but then we will use our calculator to plop out the answer. Okay, so here, of course, you recognize this is the mean. And E stands for, of course, expected value. The expected value is the mean. Expected value is the mean. Then we are going to sum up every individual X times its probability of happening. So let's see what that looks like in this case. So here we're summing up every individual X, that's negative 95, negative 5, 0, and 5, times the probability of it happening. So see what this looks like? Negative 95 times the probability of that happening, plus negative 5 times the probability of that happening, plus the next one was 0 times the probability of it happening, plus the 5 times the probability of it happening. And then that comes out, if you multiply that out, to $1.35. Now I'm going to show you a shortcut of how to write this and how to compute this in your calculator, of course. Now, FYI, what happens in terms of the shortcut of how you could write this? You can only do this shortcut if you have this table written out. Because if you have this table written out, then the sequence of events is shown. If you do not have this table written out, then you have to show all of these parts. But if you have this table written out, see, then you could just do the first and the last one, and you know how we did the binomial ones where we said plus dot 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 plus and then the last one. So again, if you have the table, you can just show the first and the last in the sequence. Now, let's talk about how to compute this without actually having to go through all the motions. And so you're going to get that out in your calculator. And so here we go. All right, so pulling that up. So we're going to go to Stat Edit, and then we're going to put in those things. So it would be negative 95 Oops, I think I did that. I did a minus sign, you know. Okay, I did the minus instead of the negative, so let's fix that. Negative 95. Okay, negative 5 was the second one. 0 was the next one, and then positive 5. Okay, next, those probabilities. So this one was 1 divided by 52. Enter, and then it turns it into a decimal, and it keeps the full decimal in there. So if you had, say, 1/3, you wouldn't be having to round it. Okay, all right, and then the one for negative 5 was 3 out of, it was the other aces, the 3 out of 52. Then this one was the 12 out of 52. And then this one was the remaining 36 out of 52. Now, FYI, these percentages have to total to 100%. Okay, that's, these percentages, 152, those four items total to 100% because this is discrete. That's the finite, that's the all of the possibilities. Okay, so that can also help you find some things out that way. All right, so here we go. We're going to go to one variable statistics, but you have to do something very carefully. So don't just rush through the answer and think you got this. Has to be done carefully. Here we go. Stat over to calc. One variable statistics. All right, now here's the catch. If you just hit enter right now, it will average and do all the statistics for your list 1, which is negative 95. So it would just do the negative 95, the negative 5, the 0, and the 5. And it would average negative 2375 because that's what those 4 numbers average together. But these are weighted averages. Negative 95, they don't all happen equally likely. Negative 95 happens 1/52nd of the time. That's how frequently it lasts. Negative 5 happens 3/52. That's how frequently it happens. So that means we have a frequency. So if you have this menu, and if you don't have the menu, I'll show you how to handle it. That is where this frequency list comes into play. You want to get the statistics of list 1, but they don't happen equally likely. They happen with list 2's frequency. So from now on, so now this is going to be in here and this is going to stick in there. So that means in the future, whenever you go and do problems, if you don't need to do L2, then you better erase that out or else it's going to give you some funky numbers that aren't correct if all you wanted to do is average list 1 equally likely. Okay, but anyway, so once you do that, then here we go. And look at there. X bar is the mean of X. X bar is the mean of X. And there we have $1.35 on average per game. So I want people to be playing all day long because I know in the long run, I'm going to make $1.35 on average every single game. Okay, so let's play. Bring it on. Now, notice there is no sample standard deviation. There is no S of X. That is because your probability distribution had 100% of the outcomes. This was not a sample. This is listing all the possibilities. So the population mean is 13, or standard deviation, population standard deviation is 13.80. All right. So that's a big deal to make sure that you get that correct. And then we'll talk about that 1380 here in just a second. All right. But I think the next part of this, I believe it says, and asks you to, I believe it asks you to interpret what that means. So after many, many trials, I want everybody to play. Come on. I expect to win $1.35 per game on average. You have to include, after many, many trials, I expect to win this much on average. Okay? Because Can I literally win $1.35 when somebody comes up and plays this game? No, that is not one of the discrete possibilities. There are only these 4 events. But once you do that average, then that average becomes continuous. It's important to catch what's happening there. Now, let's take a look at this in terms of the standard deviation. How varied is this? How what's all going on with that? What's the variability? How much could it vary each day? Okay, so look at this standard deviation. It's kind of scary looking. Here's our standard deviation, but we have to know how to write it out. So we have our square root, because remember when we would do standard deviations stuff and we would do the squaring of it so that we would have positive distances from the mean? See, I'm seeing how far away each outcome is from the average. And then I'm squaring it so that it is not a negative number times how probability of that happening. Sum all that up, and that gives you the average distance from the mean, but it was squared, so we want to then unsquare it to get the average distance from the mean, just the distance itself, not the squared distance. So that's the formula. So in this terms, you have to, again, show work with the formula. So here's how that looks. And it's very scary looking, but do remember that, well, I'm going to tell you this. On AP and on anything that I ask you to show work on, it's not going to be a ton of items, so a ton of outcomes, so you won't have a ton of things to write out. But remember, if you have that table, then you can just write the first and the last in the sequence. Okay, but let's take a look at what this looks like for each item. All right, here we go. So there's my first one. Remember, I have to pay out $95. So I lose 95 minus the mean, and the mean was $1.35. Quantity squared times its probability, which was 1 over 52. Okay, sum it up with the next one. The next one, I lose $5. Lose $5 minus my mean, quantity squared times its probability, plus the next one. The next one's a break even. Remember that? Minus the mean, quantity squared times that probability, plus the next one, I win. I bring in $5 minus the mean, quantity squared times that probability. And once I sum all of those up, that's the variance. And so then I square root it to get the standard deviation, which was $13.80. So, that's meaning like 68% of the time I'm going to be, plus 13.80 minus 13.80, above or below the mean. Usually, FYI, in the way that lotteries and casinos and that kind of stuff is desirable is because they are typically quite varied. Okay. People, you could win really big. Okay. Or you could lose small. Okay. But you could win really big. That's what's making it so desirable. But the casino is not sweating it because they know in the long run that variability doesn't matter because on average, they will always win. All right. So once you have that mean and standard deviation, then you have a continuous situation. And here's what we got here. See? So it is centered at $1.35, and then I went ahead and I wrote or added 13.80 plus 13.80 plus 13.80, and then subtracted it each time. Okay, subtracted it each time. Okay, so this then we say, okay, so this question is, as I play many, many, many trials, in the long run, this, what's happening? What's the question? Let's see. Keep in mind that this blue line here is the 0. That's where I would break even. Okay, so I want to know what proportion of the days, if we were just doing this in terms of days, what proportion of the days do I average winning, ahead, bringing in money? What proportion of the days do I bring in money? So I need to see, okay, well, that's the ones that are above 0. I am making a profit. So I put my 0 right here. So that's first, let's find that location. So that's my z-score. X minus the mean over the standard deviation. X minus the mean over the standard deviation. So that's at negative 0.1. That's pretty close to the mean. And that's what happens in gambling and casinos. Okay, but that's okay. So then to find this area here, if I norm CDF from this negative 0.1 up to infinity, I will win 46%, or I'm sorry, I will win 54% of the time. I will be ahead like 54% of the days. I'm going to be making a profit. And you may say, oh, that's not really that big of a deal. It's 54. It's barely more than half. It doesn't matter. It's more than half. So then I am always, in the long run, going to be ahead of the game. So it's worth it to me. Worth it to me because only 46% of the days I will lose. Okay? And that's kind of what is happening with the gambling. So, all right, so that was kind of a lot of information to process. And you might be interested, to find this and locate this on your formula chart, okay? So before we get into just doing some more examples and such with this next one, then I'm just going to go ahead and let us finish this video right here to kind of break it up. What this random variable stuff is and how that works to get the average and the standard deviation for that discrete probability distribution that has a finite amount of events that you can compute the probabilities for. All right, so we'll end this video right here.